We had started with the doubts from SHM from HC Verma, so we will continue with that today. So we were doing a particular question when we had to stop because the time was over and you had another lecture coming. So I'll start with that question. It's an important type of question in SHM. We'll wind up the doubts today and so that we can start with waves soon. So this was the particular question. You have two identical blocks connected to a spring kept on a smooth surface. And initially the blocks are given some compression and released from rest. So what I will do is I will generalize this question a little more by taking the masses of the blocks to be different. We'll take the masses M1 and M2. So that particular question 19 of HC Verma had the two masses the same. So we'll take a situation. In that M1 was equal to M2 was equal to M. Now initially the blocks are pushed so that the spring has some compression, let's say X0, and then released from rest. So you have to find the time period of, so first of all, you have to show that they perform SHM. Okay, question 25 is it? So show that the blocks perform simple harmonic motion and find their time period, amplitude, all these things. So this system is started from a situation at t equal to 0, where the blocks are at rest. The spring is having a compression, so this is like this. So this is the situation at t equal to 0. So what will happen is, as a result of the tension in the spring, which is kx0, they will tend to accelerate in outward direction. So after some time, suppose they reach a situation, the mean position, where the spring is back to natural length. So the block's acceleration is 0. So this is the mean position. At this state, this one has 0 acceleration. This one has 0 acceleration. Because it's at natural length. Now, because the springs are pushing them outwards here, you can see they are having accelerations A1 and A2. So by the time they reach the mean position, they also have some velocity. Now you will see that the center of mass is stationary throughout, because the external force on the system being the blocks plus the spring, is equal to 0, and therefore acceleration of center of mass is 0, and the center of mass is at rest initially. So if it is at rest initially, so both the blocks are at rest, okay, and its acceleration remains 0, so the center of mass will remain at rest. Okay. So that's why we can see over here that m1 v1 will be equal to m2 v2 because center of mass is at rest. Similarly, here m1 a1 is equal to m2 because acceleration of center of mass should be 0. Okay. Now let us assume that from this position it comes somewhere here where the spring has got elongated. So from this position, we've reached a situation where this one has got displaced by x2 and this one has got displaced by x1 and the spring has got extended by x. So again, because the center of mass is at rest, you can see that m1 x1 will be equal to m2 x2 because center of mass is at rest. Okay. And x1 plus x2 is x, the total extension of the spring. In terms of force, what is happening is this block is experiencing tension like this. This force, this block is experiencing tension like this. So they have accelerations A1 and A2 like this. Okay. So next what we'll do is we'll write the FBD equation of M1 and M2. And from that we'll understand that they are doing SHM. Okay. So we will make the FBDs of these two blocks at this particular instant of time. Okay. So next step will be from the FBDs. Of blocks M1 and M2, we'll show that they are satisfying the SHM condition. We'll come to that, but first note down up to here. Okay, so now what we do is, have you tried making the FBD and seeing if the SHM condition works out? Okay. If you've done that, then you will see that you will get an equation which is slightly different to the SHM equation, because on a block of mass M1 which is having an acceleration A1, the spring force is Kx. Okay, so we are getting Kx is equal to MA1, but here A1 is what? It is minus d2x1 by dt square. Okay, it is not d2x by dt square, because remember x is x1 plus x2. So we have to relate now for SHM. We have to relate d2x1 by dt square with x1 and not x. So what do we do? That's where these equations come in. Equation 1 and equation 2. So this is our equation 2, and from equation 1 we have m1 x1 is equal to m2 x2. That means we can substitute x1 is to x2 as m2 is to m1. So now from these we can solve, and we can say that x1 is equal to m2 upon m1 plus m2 x, okay, and x2 is equal to m1 upon m1 plus m2 x, as be the case. Okay, so this is the free body diagram for this block. Okay, I'll come to the second block also. So now in this equation we can substitute this. Okay, so from this we are getting this. Okay, so we can substitute this. So we'll have k into, now x can be substituted as m1 plus m2 upon m2 into x1. This is equal to minus m1 d2x1 by dt square. So now you see you are getting your SHM equation, that d2x1 by dt square is equal to minus k into m1 plus m2 divided by m1 into m2 into x1, or d2x1 by dt square is minus of omega square x1, which is showing you that this is the SHM condition. Or like that we'll find for the second block also. Okay, so this is the SHM, okay, with additionally the precondition that omega square for this block's SHM. So this shows that block M1, okay, so M1 performs SHM with omega equal to square root of k into M1 plus M2 upon M1 M2. So time period equal to 2 pi under root. Okay. Now like that we'll do for block M2 also. In fact, you try it out, note this down and try it out, and you will see something interesting when you make the video of this M2 one. Okay. So just make sure you're clear with the steps over here. So in question 25, what was happening? In question 25 of HCV, M1 is equal to M2. So X1 is equal to X2 equal to X by 2. So this equation would have become that d2x1 by dt square is minus k by, or 2k by m into x1 into the next. Okay. For that question, this block's SHM is with omega square equal to 2k by m, or time period equal to 2 pi under root m by 2k. Because that's a special case where m1 is equal to m2 is equal to m. But suppose we have some other situation where m1 and m2 are generic, they can be any values. So then this is the general formula for the time period for such a system. Okay, so Tandresh, have you tried the FBD of the second block? Try to follow the same steps for the second block. Remember over here, X1 is the displacement of the block M1 from the mean position. Okay, from its position when the system is at mean position. Similarly, X2 is the displacement of M2 from the mean position. So that is why it's important to be able to write their accelerations A1 and A2 in terms of their displacements X1 and X2, rather than in terms of the overall extension of the spring, which is X. Okay, very good. So you're getting the same omega square, na, Tantresh? Let's just work it out once over here. So you see that on the other block, on M2, it is displaced by X2 from the mean position. And in that condition, there is again force Kx acting on it. So its acceleration A2 is like this. So Kx is equal to M2A2, where A2 is minus d2x2 by dt square. Now again from equation 1 and 2 above, we had got this relation that x2 is equal to m1 upon m1 plus m2 x. So So just invert this equation and substitute that here. So this becomes that k into x, which can be written as m1 plus m2 upon m1 x2 is equal to minus m2 d2x2 by dt square. So you get your SHM equation that d2x2 by dt square is minus k into m1 plus m2 divided by product of m1 m2, which is exactly the same value of omega square as for the above block. Okay. So this is the SHM condition. So this is SHM with omega equal to square root of k into this kind of term. So time period the same. Okay. So from this, what we do is we develop a generic formula for a two block system like this, where we introduce a term called reduced mass. This term m1 into m2 upon m1 plus m2. This is called the reduced mass of a two block system like this. So this is a general formula we develop, and SHM of such a system always has omega square equal to k divided by reduced mass. So we'll do a quick numerical example of this. So in this example, M1 we are taking as suppose 3 kilograms, M2 as 6 kilograms, and the spring constant as 8 newtons per centimeter. And initially, the blocks are pulled apart such that the spring has an extension of 1.2 centimeters and released from rest. Find time period and amplitudes of each block's SHM and find the maximum compression of the spring, and also find maximum speed and acceleration of each block during the SHMs. Okay. So now in such a problem, you can directly use the reduced mass formula. Once we have gone through the derivation of it above, you can directly use the reduced mass formula. So this is the system with these values given. And initially, this is the condition given. This is 1.2 centimeters. Okay? It's released with an initial extension of 1.2 centimeters. Okay, Diti, I'm scrolling up a bit. Hope everybody's got the data of this question written down, so you can start. I mean, you can continue working on the question. This part or above? Okay. Yes, good, Pankaj, that's correct. So we can just do this question directly using the formula we have derived before. But just for the understanding, if this is the situation of mean position, where the extension of the spring is 0, then at some general time, it says like this. So this is the natural length situation. So this is when both of them are at mean position. So this is when the spring has some general value of extension x, such that individually these blocks are having a displacement of x1 and x2 in these directions. And because of the spring force, they're having accelerations a1 and a2. So we've seen that these are the FBD equations. Then these are the constraint relations from center of mass concept. So solving this and this together, we get that d2x1 by dt square is minus omega square x1, and d2x2 square, I mean d2x2 by dt square is minus omega square x2, where omega square is k divided by reduced mass, where the reduced mass is product divided by the sum. So here omega square will become 8 into 10 raised power minus, sorry, 10 raised power 2 divided by reduced mass. Now this will become 2 kilograms, as you can see. So omega square is 400. So omega will come out to be 20 radians per second. So time period will come out to be 5 by 10 seconds for both the SHFs. Now the next thing is we have to look at the amplitude. So both blocks are in SHM such that x1 is some amplitude into sine omega t plus pi 1, and x2 is some amplitude a2 into sine of the same omega but let's say some phase constant phi 2, where omega is 20 radians per second. So now the next thing is we have to find A1 and A2, the individual amplitudes, and possibly phi 1 and phi 2 also, though in the question I have not asked. Okay. So how will we get A1, A2 and phi 1 and phi 2 from the initial conditions? So A1, A2, phi 1, phi 2 will come from initial state, that is x1 at t equal to 0 was how much? X2 at t equal to 0 is how much? Okay. And initial velocity at t equal to 0 was how much? Okay. So all these things at t equal to 0. So from that we'll get these phase constants and these amplitudes. Okay. So now just try to work this out. So you'll see the same relation holds between A1 and A2 that holds in general between X1, X2 or V1, V2 or A1 and A2. And the fact that comes from the center of mass being stationary. Yes, very good, Tandresh, that's correct. But only I think M1 is the heavier mass. No, M1 is the lighter mass. Okay, that's correct. Then the values are correct. Very good. M1 is 3 kg and M2 is. So see here, we know that at t equal to 0, x naught's value is how much? 1.2 centimeters. Now remember, in general, we had x was equal to x1 plus x2, and m1 x1 was equal to m2 x2. So this told us that x1 is to x2 was actually 2 is to 1. So using these equations, you can see that x1's initial value, but plus x2's initial value is 1.2 centimeters. Okay. And x1's initial value's ratio with x2's initial value is 2 is to 1. Therefore, x1's initial value is 2/3 of x naught, or 2/3 of 1.2 centimeters, or 0.8 centimeters, and x2's initial value is 1/3 of this, so 1/3 of 1.2 or 0.4 centimeters. So that is the thing. Okay. And we also know that u1 is 0, and okay. So from this relation, we know that v and similarly from this we have so these things, okay. So a1 sine phi 1 is equal to 0.8 centimeters, and a1 omega cos phi 1 is 0. So this pair of equations is telling me that phi 1 must be pi by 2 and a1 must be 0.8 centimeters. So x1 must be 0.8 sine omega t plus pi by 2, or cos omega t. Okay. And similarly, so this is also pi by 2. So x2 as a function of time will become 0.4 cos omega t. And from that we can see that extension of the spring at any time is x1 plus x2. So it is 1.2 cos omega t. So the length of the spring, it ranges between L plus x's maximum value to L minus x's maximum value. So maximum compression is also 1.2 centimeters. Maximum extension is also 1.2 centimeters. So this covers all the various type of questions that can be asked with a reduced mass system. So not necessary in one question at JEE level, so many things will be asked. but you can be asked any of them. So you should know how to analyze all these things. Okay. So we'll come to the last part where we are looking at maximum speed and acceleration of the blocks also. But this is the part where we calculate the individual amplitudes and also the maximum compression of the spring. Okay, people. So hope this question is fully clear now. And this type of question involving reduced mass. Okay. Now let's move on to some more questions from HC Verma. Maybe any other doubts after question 25? Just let me know or post it on the text message. Otherwise, I'll suggest some questions. Okay, good. 26, all right. 29 and 42. Okay, we'll discuss this. So let's start with 26. So we have this kind of a system. From some ceiling, we have tied two threads. To suspend sort of rectangular slab kind of thing like this. And they are of length L each. So for small angular displacement, we have to find the time period. Slightly displaced in its plane, keeping the strings tight, so show that it will perform SHM. So from this position, in the plane of that rectangular sheet itself, if we give a slight amount of angular displacement, we're talking about something like this. So for small angle displacement, we can see that the center of mass we have gone from this position to this kind of a position. So you can see that if we are able to show that the SHM condition is satisfied, we can find the time period of oscillation. Just a minute. So in the equilibrium condition, we can see that the tension balances the weight of the object. This is equidistant on both the sides. So the tensions are equal. So this is a mean position. So when we take it to an angular displacement of theta from the mean position, like I'm showing in this diagram here, for small theta, what will happen is this tension will more or less be equal to T naught, equal to mg by 2 for small angular displacement theta, such that cos theta is tending to 1 and sin theta tends to theta. Okay, so for this kind of condition. So you'll see that in the FBD of this object, there is mg acting like this, and there is this 2t which is acting like this. So it's having an acceleration in this direction, which is like a tangential acceleration. So 2t sine theta becomes mass into tangential acceleration. Now, if we assume that this horizontal displacement of the center of mass is x, so x is again very nearly equal to L theta. This is r. So this is r theta. So x is nearly equivalent to r theta. And r, as you can see, will be L plus a by 2. So here for small theta, sine theta can be approximated as theta, t can be approximated as t naught, which is mg by 2, and tangential acceleration will become minus d2x by dt square. So doing that, this equation will become 2 times mg by 2 theta is equal to minus m d2x by dt square. And then further we have the relation for theta. We saw that x was equal to r theta. So theta becomes there's no square here. So ultimately we get our SHM equation like this, that d2x by dt square is equal to minus of g divided by L plus a by 2 into x. So this is our SHM equation. So I'll just minimize this a little, try to understand all the steps and note them down if required. Okay, very good. So next we will move on to question 29, I believe, after this. Yes. So we're going to do 29, 31, 42, 41 also. 39 also. Okay, so note this down and go through question 29 we'll discuss. So realize one thing, question 29 is not a problem of SHM. That particle will not be performing simple harmonic motion. However, it will be performing oscillation. Okay, and the time period of the oscillation will have to be calculated by your normal Newton's laws of motion method. Okay, let's move on to question 29 next.
So in question 26, the answer behind is given under L. There is
Sorry?
no a term is not there.
Okay. So here the time period is coming 2 pi under root L plus a by 2, right? Divided by g. Okay. Whereas the answer is probably given 2 pi under root L by g, right?
Yes.
So there they have neglected a by 2 compared to L. That's one. Okay. Okay, let's move on to question 29 next. So 29 has a situation where there is like asymmetrical slopes, 45 degrees on one side and 60 degrees on the other side, but frictionless surfaces. You can see that it's asymmetrical. And from some height of h equal to 10 centimeters, we release a particle from rest. So what happens is, as it slides down, it's having an acceleration a1 on this side, let's say, of g sine 45. It's a frictionless surface. So g by root 2, and it reaches here at some time, let's say t1. So half a1 into t1 square is equal to this displacement s1, this total displacement, which will be equal to how much? It will be h upon sine 45. So half g by root 2 t1 square is equal to h to 1 by. Okay. So from this we'll get t1 as square root of h by g. Now what is happening from this point onwards? It climbs like this. You'll realize from work energy, it will come to rest at the same position. And then it will also then come back. Let's say later it comes back and again reaches this position. So here was T1. So this position is some T1 plus T2. Okay. And so when it's back over here, coming back and it reaches here, the time will be T1 plus 2T2. And then from there, as it comes back here, going up like this, the time will now be 2T1 plus 2T2. Okay. So the time period of the motion is 2 of T1 plus T2. And that you already calculated. T1 is this much. So now we need to calculate T2. So for T2, just look at the third part of the motion, not the second part, but the third part. That is when it has reached this maximum height. From work energy, you'll see it will reach the same height of 10 centimeters as it reached on that side. But it's at rest. Okay. And then it reaches here. So this was at time T1 plus T2. This is at time of T1 plus 2T. So during this time of from the highest point to the lowest point on the second slope, its acceleration is again g sine 60 in this case. So root 3 by 2g. Okay. And the displacement S2 is h by sine 60 or 2h by root 3. Okay. So again, half a2 t2 square is equal to s2. So half of root 3 by 2 gt2 square is equal to h upon 2 root 3. So from this T2 will come out to be how much now? T2 will come out to be square root of 2h by 3g. So the total cyclical time period will be 2 times T1 plus T2. So it will be 1 plus 2 by 3, something like this. So it is basically application of Newton's laws to find the acceleration and then kinematics. Acceleration on a smooth inclined plane is g sine theta, as you know. Make a note of this. Next we move on to 30th and 31st question. Yeah, we will do all that answers. Okay, now before I forget, in that previous question, we had also we wanted to find out the maximum speed and acceleration. So I'll just quickly take you through the formula. So maximum speed and acceleration of each block. So just remember, for M1, maximum speed will become A1 omega and maximum acceleration will become A2 omega, sorry, A1 omega square. And similarly for M2, the maximum speed will be A2 omega and the maximum acceleration will be A2 omega square. Nothing else is required. We found out A1, A2 and we know omega. So just add this to that solution. That was the last part of the question, the fourth part. Okay, now question 30 actually you'll realize is the same as that question only. Because in question 30, indirectly the same thing is happening. Okay. We have this platform with a block of certain mass. And a spring of certain constant K. Now this is having mass capital M, this is having mass small m. Now see that suppose at this point of time, it was having some compression. So as it goes from here to the mean position, this would have displaced by x1. This would have displaced by x2. Spring would have come back to natural length. But displacement of center of mass would remain at rest. So this is the same as this kind of system. The same as this. Okay, so Tantresh, hope this question is clear. Okay, very good. Now moving on to 31. Now 31 is the one which is little different because it involves application of rotational mechanics actually. Okay. So why question 31 is different is because there is kinetic friction acting, but at the same time there is SHM happening. Because generally speaking, an oscillating system cannot have kinetic friction because that will dissipate energy. Okay, and in any oscillation, the energy should remain conserved. But here what is happening is that there is some external agent who keeps the two rollers moving at constant angular speed. So that external agent is supplying some power to the system. Okay. And that power is compensating for the loss in kinetic energy. So this is rotating at constant angular speed omega. This is rotating at constant angular speed omega. And this surface has coefficient of friction mu. And also the distance, just Okay, so coming back to this, yeah, so there's 30th question, the same thing. Now it is from the mean position. So the spring is attached to both of these. Na? The spring is attached on the left hand side to an object which has mass capital M. You understanding? Na? On the left hand side, the spring is attached to an object which has mass capital M. On the right hand side, it is attached to an object which has mass small m. So understood? Na? So if the spring is, for example, compressed at this point of time, it's pushing this like this, it's pushing this like this. So this is tending to accelerate like this. This is tending to accelerate like this. So it is that same situation. Okay, good. Okay, now coming back to this. So यहाँ पे क्या हो रहा है? Some external agent continues to make this rotate at constant omega, regardless of the loss of kinetic energy because of slipping. Okay, so omega is maintained constant by some external agent. Okay. Now what will happen is that initially at some time, if the center of mass is here, such that it's equidistant from both these points of contact, then at that stage what will happen? The normal reactions will be the same, because torque has to be balanced now about the center of mass. So here, suppose this normal reaction is N2, this normal reaction is N1. So the friction acting on the plank here will be mu N1. The friction acting on the plank on this side will be mu N2. Okay, now at this particular position, you will see that N1 plus N2 has to balance mg. Okay. And when we are doing net torque about the center is 0, you will see that N1 into L by 2 is balancing N2 into L by 2. So the torque balancing equation shows you that N1 is equal to N2, which is equal to mg by 2. So therefore, mu N1 and the second one's friction, they're equal. So therefore, net force is 0. So it's the mean position. Now, if we displace this from the mean position such that this is happening, suppose we displace it to the right of the mean position. The center of mass has come here now. We displaced it by x. Okay, but the two rollers are at the same position. So then the point of contact of N1 and the point of contact of N2, they are not equidistant horizontally from the center now. This has become L by 2 minus x. This has become L by 2 plus x. So you can see that now N2 would have become greater than N1. So as a result of that, this friction would have become greater than this friction. And so the block will have an acceleration in this direction. So now what is happening? Your N1 plus N2 is still mg, but net torque about the center of mass is 0. So N1 into its momentum, that is L by 2 plus x, is balancing N2 into L by 2 minus x. Clockwise torque, anti-clockwise torque. This is your torque balancing equation. So from the second equation, you can see that N2 minus N1 into L by 2 is equal to N1 plus N2 into x. Now substitute this from the first equation. So you have N2 minus N1 into L by 2 is equal to mgx. So the difference of the normal reactions is equal to mgx upon L by 2. So this. Now along the horizontal, you can see that the net force is F2 minus F1 is equal to ma. where A is minus of d2x by dt square. So that is mu n2 minus n1. Okay, so now substitute this. So our SHM equation is here. Okay, so make a note of this, people. So this is the torque balancing concept is important over here. From that, you're understanding that when you go away from the equilibrium position where the center of mass is at the midpoint of the two rollers, okay, you're disturbing the balance of the two normal reactions. One normal reaction is becoming greater than the other. So accordingly, that means friction is dominating, and that net frictional force is providing the restoring force, which is trying to restore it back to the mean position. So it's an SHM because that restoring force comes out proportional to displacement. Okay, so let's move on now. This was question 31. Next, we're doing question 39, 41. So let's do on this. Okay, so spherical ball of mass m and radius r rolls without slipping on a rough concave surface of large radius capital R. Make small oscillations about the lowest position. Find the time period. Okay. So let's say this is a large hemispherical surface. So first of all, I'll so radius is R. This is the geometrical center. Now, a small tiny sphere, if we keep it here, you can see that it's at equilibrium or mean position. But the moment we take it to some angular position like this theta, you can see that it will start rolling because of the combination of forces acting on it. So now making the free body diagram of that part, making the FBD of that section a little more clearly. So what we'll see is when our small sphere is at this sort of angular position, at that point of time, the forces acting on it will be its weight, normal reaction, and friction acting such that its center of mass has a tangential acceleration like this, and about the center of mass there's a angular acceleration such that it's rolling. It's a rough surface. Now, while it is rolling, this angle is theta, suppose. So that is the angle that the tangent to the surface makes with the horizontal. So that will be the same as this angle theta, where this is 2. So we'll see we have the relation that mg sine theta minus friction is equal to ma. Friction into r is equal to I alpha, and E is equal to R alpha. The rolling condition, the rolling constraint. Okay. So solving this system of equations will now give us the SHM condition actually. So we'll see that this second equation will become that F into R is equal to 2 by 5 mr square into A by R. And then substitute that in the first equation. From this we'll get A is equal to this is how far we'll reach. Now we have to apply the small angle approximation. So theta is small. So sine theta will approximate as theta. Yeah, solid sphere, no, but that's why 2 by 5 mr square. Then solve this equation, take this to that side. 1 plus 2 by 5 हो जाएगा. So that's how. Yeah. So 2 by 5 MA only. R is cancelled, beta. There's one R on this side and one R in the denominator. This equation, no? Friction into R. Moment of inertia is 2 by 5 mr square and alpha is E by R. No? So one R cancels like this and one more R cancels like this. That's how we get. Is it clear, Tej? Okay. Okay, so this is the relation. Now next thing, so now what we'll see is that this distance, suppose this is S, that R plane. So theta is S by capital R and A is minus d2S by dt square. So this equation can be written as minus d2S by dt square is 5 by 7 g theta, because sine theta is approximated as theta, and then further minus d2s by dt square is equal to 5 by 7 g into theta will be written as s by r. So we have the relation that d2s by dt square is minus 5 by 7 g by r into s. That is the SHM equation. So omega is square root of 5g by 7r. Time period is 2 pi. Okay, very good. Okay, now question 41 and 42 are based on the same principle. So we'll discuss that. Okay. And we can work out both the problems in one shot. Okay, fine. We'll pick up in the next lecture. Okay. So I'll tell you what, for the question 41 and 42 now, just do one thing, revise before the next lecture. Okay. Gravitational field inside a solid sphere. That formula, do a revision of it. You'll see that the formula of gravitational field versus distance from the center of a sphere is like this. It's linear inside and hyperbolic outside. So this one, do a revision of that. That will help you understand question 41 and 42 both. They're based on that. Okay, so then we'll complete the doubts of all this, and a couple of things are remaining in SHM. In the next lecture, we'll do combination of SHMs. Okay. We'll also do spring pendulum, torsional pendulum. So two more types of pendulums and damped oscillations. But these are all small things. They'll just take a few minutes. So doubts will be the most important things. Yeah, so we'll discuss. No worry. In the next lecture, we'll finish all that and discuss. Those are very less in number and very easy questions. So that's it for today's session, people. Wish you all the best. Have a nice day. We'll pick this up in the next week.